Okay, welcome all. Today I will talk about different relaxations of the interlinear program that we have previously used to find the map solution in undirected graphical models. One relaxation will be in the primal, so in the domain of the original indicator random variables. The other formulation will be in the so-called dual space, which has some advantages for optimization that we can leverage. And either today or next week, depending on how quick we are, I will show that actually these two relaxations are equivalent, but the dual formulation has some advantages. So let's start with the Primal LP relaxation. So if you go back a few weeks, we saw that we could minimize over one hot indicator variables. So we had an indicator vector associated with each random variable, and one element of that indicator vector was 1 and all others were 0, and the indicator vector told us which state this random variable takes. So we have a set of vertices V. We sum over all nodes in this graph. We sum over all possible labels K from the label set L. This was the indicator vector. Mu I is the indicator vector for node I, and K is its kth element, so for the kth state. This was the unary factor, and then we have the pairwise factors. We sum over all pairs ij from the edge set E, and over all states K and L that these two random variables can take. And now we need a couple of constraints. We had introduced indicator variables for the unary factors and for the pairwise factors, and now we have to make sure that the two agree. Okay, and we have two sets of equations here because the edges are ordered. Okay, we have two sets of equations because the edge ij is not the same as the edge ji. Okay, and then we had the integrality constraints. So we said that mu ik must be a binary vector, and we want exactly one of these to be on. And we had mu ijkl that should also be binary. Okay, and if we look at all of this, so this was all of these, the first few constraints are easy, and the last two are hard. Okay, because the first ones give me a convex problem, and the last two lead to the problem being non-convex. So as it stands, this is an ILP formulation. an integer linear program. Linear because the objective is linear and the random variables over which we optimize. The constraints are also linear, and we have these integrality constraints. Now, to make this problem easier, we can approximate it as follows. We can delete this and simply say that mu I of k should be no less than 0, and mu ij of kl should be no less than 0. And then this becomes a linear program, much cheaper. And this is a relaxation of the original problem, because solutions that are feasible under the original constraints are still feasible under the new constraints, but not vice versa. So we now have a larger space of admissible solutions. Let's look at these spaces. So the feasible solutions of the ILP are a set of integers so I'm showing some integers here, and actually we have a binary problem. So let's say we only admit the states 0 and 1. So the states 0 and 1, let's say, would be those if we had only 2 random variables. But now we have all these additional constraints, and so perhaps in the end, let's say that I have in this example, let's say I have 3 feasible solutions of the ILP, this one and this one and this one. And these feasible solutions, they span the marginal polytope. So this marginal polytope, this is the convex hull of the feasible solutions. Note, these are not optimum solutions. We just have a single or few optimal solutions, but here we're talking about all feasible solutions. Okay, so in this case, the marginal polytope would be this. And by the way, if we had all the, if we could find these constraints here efficiently, then solving the integer linear program would amount to solving a linear program, because we know that the optimum solution must always be in a corner of my polytope. The problem is that these marginal polytopes may have very many facets, so that we might need an exponential number of constraints, and we don't want to solve a linear program with an exponential number of constraints. Okay, so that was the marginal polytope, and now we can relax the constraints and obtain a larger solution space. Let's say, for example, remember that this is a very low-dimensional sketch of a high-dimensional phenomenon. Okay, but anyway, the body that you see now, and which I'm indicating here in yellow. So this thing is an outer relaxation of the marginal polytope, and this is called the local polytope. It's called local polytope because we do respect these local consistency constraints up here, but we omitted the integrality constraint. again, from my sketch, you can already see that this local polytope, it may, but it need not, share corners with the marginal polytope. So optimizing over this local polytope is relatively easy because this is just a linear programming problem. Optimizing over the marginal polytope is hard because it's an integer linear programming problem. And now I did not indicate in this picture where my cost vector is pointing. This depends, of course, on the data I observe. So for example, if my cost vector is pointing in this direction, then the solution found by the relaxation or by solving the ILP will be different. However, if my cost vector is showing or is pointing, let's say, in that direction, then the solutions will happen to coincide. Okay, and then my linear programming relaxation will give me the same solution as my full problem. Can you tell me how I recognize if this is the case? How can I recognize that my relaxed solution is in fact the solution to the original problem? Yeah?
The solution of the relaxed problem is an integer and not a
Exactly. So typically we have very many indicator variables mu, and if all of them happen to be integral, then we know that we have not only solved our LP, but we have even solved the original problem. And we're done. Okay. So what we see from this picture, or also from the argument that the relaxed solution has a bigger search space, or the relaxed problem has a bigger search space than the original problem, that means if I, here in this formulation where I want to minimize my objective, the relaxed solution will always have an energy that is lower, or at most as high as the integral solution. However, it will be fractional, oftentimes. Yeah? So we find that LP of psi, the solution of the linear program, is upper bounded by the energy of the integer linear program. And we have equality if and only if we get a fully integral solution, and then we know that we have actually solved the original problem. Sometimes I can have degenerate solution, yeah? So I'm writing if at least one of our optimal solutions in the degenerate case. If it is fully integral. Okay, so this was an LP relaxation in the primal domain. Any questions so far? Okay, then we turn to the dual domain. Yeah. I wrote that we have equality if and only if at least one optimal solution of the linear program is already integral. Oh, okay. I understand. Okay? Good. So next, dual decomposition. I will start with a different formulation and at the end show that actually they are the same. Yeah? So I am writing our energy minimization problem, where this time I'm making explicit not only the dependence on the current solution X, but also on the potentials, because I can always rewrite this as a sum of energies, provided that the energies sum up to the original problem. I can rewrite this as minimizing an energy function depending on potentials psi1 plus an energy function depending on potentials psi2 and so on. Provided that these potentials sum up to the potentials of the original problem. And this whole thing is a reparametrization. So I could build if we think of our typical MRF, I could, for example, say that I take this whole thing and I write this as a sum of two different MRFs. Note that I use the same labeling everywhere. Yeah, so this would be the label x1, and I would have the label x1 here and the label x1 there. But this would be here my potential psi1, 2, the original one, and this would be psi1, 2, 1, and this would be psi1, 2, 2. Okay, and the requirement is that psi1, 2 equals psi1, 2, 1 plus psi1, 2, 2. And the same holds for every potential. Okay, and provided that I use the same labeling, this is just a more complicated way, or there are of course many possibilities to reparameterize. I could, for example, split this in the following sense that I could delete, let's say, this potential in the one graph and let the other graph consist of all other potentials except the one that I have deleted. Yeah, so this would be another possibility, and so on. Yeah, so there is an infinite number of possibilities. I can either assign a single potential just to the one or just to the other part of my decomposition, or I could say I use 1/2 of the potential here and 1/2 of the potential there, and so on. Okay, this is so far this leaves us many degrees of freedom. Okay, and now I will still rewrite this in an equivalent problem, but this time making explicit that actually we have different random variables here. So I want to minimize over x1 and over x2 and so on and over xt. the same objective as above. Excuse me, I should use superscript, not subscripts here. Because now I admit to use different labelings for my different subproblems so long as they agree. Okay, so the first condition is again that the potentials must sum up to the original one. And now we have a new condition that my complete labeling of the problem x1 should be the complete labeling of the problem x2. All these labelings must agree. And if I impose this condition, I can introduce an extra set of labels for each of my new subproblems. But this is still a perfectly equivalent optimization problem. And now we're going to make the crucial simplification, namely, in the next step, we will omit this condition. And by omitting this condition, I can lower bound my original problem as follows. So by omitting the condition, I have decoupled these individual optimization problems. So I can now use each minimization only over its own labeling. And I only keep the first of my two conditions. So if I want to summarize all of the above, I can write more compactly what we have found, namely my original optimization problem is lower bounded by a sum of optimization problems where the solutions of the subproblems need not agree. Shall I write it down in words also? Or is the equation clear enough? Matthias, I made a mistake?
I'm not sure. I just understand the smaller e and equal to, because we are minimizing, and this is now the coupled formula. And I thought that then it should be bigger than the optimal solution. So above we have the optimal solution, and our approximation to the coupled one is now smaller than the optimal solution. Or do I understand it?
So we here have a minimization problem, and if I allow each of these minimizations to occur separately, then they can reach potentially lower values than they can if I restrict them somehow. Yeah, so this is why the inequality is this way, not the other way around.
And this condition that is crossed out means that they all had to be the same, the labels first.
Yes, previously I had, so in this picture here, I had said that on the right-hand side, I used the same labeling x1 for node number 1. And this was written in, so this was the picture belonging to this line here. Now, in the line below, I introduce a new or a redundant set of random variables. So I say there is an x11 and an x12. However, I demanded that x11 be the same as x12. So this was this equation here. And now in the third line, where the inequality comes, I allow them to be different. So now I allow distinct labelings for the replicas of my subproblems. Okay? And the strength of this approach lies in the fact that I can choose any decomposition I like. So I can, for example, if I have a huge problem, which let's say doesn't fit into memory, then I can decompose it into small parcels and optimize each of the subproblems separately. Unfortunately, the solutions of the subproblems need not agree at their boundary. Yeah? So let's say that I have an original problem which is vast, let's say a huge image, and one way of chopping up the problem is to say that my psi1 is identical with the original psi in the upper left corner of the image, but I take 0 everywhere else. And for the next problem, I only take those potentials from the original problem and set the rest to 0, and so on, provided that altogether they sum up to my original potentials. Now, if I have a little bit of overlap, let's say I have an overlap of 1 column of pixels between the first two, then I have no reason to assume that the solution that I find in the subproblems will be identical along that 1 column of pixels. So just having a lower bound is not helpful because the lower bound can be very loose. So in the extreme case, I would simply chop my original problem up into all its individual factors and ignore the interplay between them, and then I have subproblems that are trivial to solve, but they don't agree. So I have an interest in making this inequality as tight as possible. I want to increase the lower bound by as much as I can. So we have 2 extreme cases. One extreme case is where I take just a single factor in every subproblem, and this is actually almost the case that we're going to study in a minute. And then each of the subproblems is trivial to solve, but if I put together these solutions, I will find that either they disagree when I have overlap, or if I've decomposed such that they share no random variables, then I will actually find a poor overall energy in most cases. Or another extreme case would be, so then my lower bound will be very loose. Another extreme case would be that I take the first subproblem to be the original problem, and I make all other subproblems 0. Then I have not changed anything, and my lower bound is tight. However, my new subproblem is as hard to solve as the original one. And now the interesting cases are between these two extremes, and this is where the most successful algorithms are. Remember from yesterday that we now have a new hammer. So one hammer we have is graph cut, another hammer we have now is belief propagation. And one thing we can do is we can take this original problem and decompose it such that the hammers that we have fit these sub-problems. So, for example, a very successful strategy is to decompose the sub-problems into trees. A simple strategy is to say, I take my first subproblem to be just a single column of the image. The second subproblem is the next column, and then afterwards I do the same thing with rows, so that I have one subproblem in the end for every single row and every single column. And yesterday we have seen how along such a row or such a column I can solve the problems exactly just using dynamic programming. What remains, however, is to assure that the solutions that we find agree as much as possible. And making them agree as much as possible, I will try and explain it qualitatively first. So I'm trying to give you the intuition here. Let's say I have a let's say these are the states of random variable xi1, and these are the states of my second incarnation of node number I, and I now have, let's say, a unary potential associated, or let me not, okay, I'm going to write energy here, and I'm going to be a bit vague about what exactly I mean by that. So let's say that in its replica, these are the energies which I find for the different states of this random variable. So in this case here, my random variable has 5 states, and the optimum solution of this first random variable is going to be state number 2, because it has the lowest energy. Similarly, I find energies for my second incarnation of the random variable, and it will have its optimum solution here, because the 4th state has the lowest energy. So what I can do now is I can start changing the parameterizations between my 2 subproblems such that I'm trying to push this energy up, and I'm trying to push that energy down. And here, vice versa, I'm trying to push this energy up and that energy down. And the motivation is that hopefully we will reach a break-even point where the 2 can agree on which state we actually want to assign to node number I. So we're going to change our reparameterization to make this lower bound tighter. So the goal is to first choose some reparametrization or some decomposition. We choose a decomposition of the original potentials, and we then shift around energies, and putting quotation marks here, or shift around potentials between the subproblems. To make them agree on a labeling. And this will tighten my lower bound. Yeah.
Is it also allowed for the labels to change to another one? For example, we have the one subproblem says 2, one says 4, then we change energies and then maybe both agree to 3? Or?
Yes, that can happen, that so one has label L, one has label K, and then in the end we find a label M for both. It may also be impossible to achieve agreement between the two labelings. So if we can reach agreement everywhere, then we have closed our duality gap. If we have disagreements, then there is some gap. So I'm setting up a in one particular way of shifting around potential between the subproblems. So let's look at our minimal loopy graph. I can rewrite this as follows. So I should put a, or you can think a plus everywhere.
Sorry?
Yeah.
On the left, you just omitted the pairwise potential.
Thank you. And now we can start pushing around mass. For example, I can say that this guy here, psi I of xi, is going to give a bit of its energy to this pairwise potential here. And so I'm shifting some energy from here to there, and likewise from here to there. So I have psi j of xj minus delta ji of xj. And And by doing so, I simply obtain a different reparameterization. I have conserved energy because I have subtracted some amount here and added it there. It should be a plus. Thank you very much. Okay, so I have introduced these new dual variables delta. Yes?
Why is it possible to shift the unit potentials into
Why is it possible to shift units into pairwise? You can always subsume lower order potentials in higher order ones. Yeah? So if you think of a pairwise potential, and if I now want to add this, then I multiply it in this case with I take the outer product here with a vector of ones, and then it is matrix shaped, and I can add it there. To make this even go away. Okay. I could have added, extra unaries here to make it clearer. All right, good. So I've introduced these new variables delta, and we now want to somehow find an optimum choice of delta. And I'm giving this a suggestive name now, L for Lagrangian. I will argue later why this is a Lagrangian. And we now create as many instances or replicas as we have random variables in our set of vertices. And again, this is a very particular decomposition that I'm choosing now. Many others would be possible. So I'm passing on some mass to all adjacent pairwise potentials here. And my pairwise potentials receive some mass from all, from the two adjacent ones. Good. Okay, so we now have introduced these new variables delta, and we now want to maximize over these new variables. Because the thing on the right-hand side is gives us the energy of the lower bound, and now we want to push this lower bound as high as possible.